This is joint work with Cameron, Zhao, and my advisor, Anastasios Kyrillidis at Rice, and Zhao from UT Health. This work is Demon Momentum Decay for Improved Neural Network Training. The motivation is relatively straightforward. A lot of areas of deep learning have advanced a lot in the last few years. For example, in NLP, there are a lot of advances with transformers and BERT and GPT. But one of the fundamental tools for training these deep neural networks has remained the same, which is optimizers. So there are two main optimizers, SGD, stochastic gradient descent with momentum, and ADAM on the bottom left and bottom right here, which have remained two of the most popular optimizers, even though they were proposed a long time ago. For example, ADAM was proposed in 2014, and SGDM was around far before that. And optimization is one of the critical parts in deep learning because it's a fundamental tool for training the neural network. And a lot of compute is wasted on hyperparameter search. So one of the typical ways you'll do hyperparameter search is through a grid search, but this doesn't scale well. And thus the holy grail is achieving strong performance with decreased dependence on hyperparameter tuning. To this end, we propose Demon. Demon is a simple momentum decay rule motivated by decaying the total contribution of the gradient to all future updates. And there is limited overhead and additional computation. In particular, we observed that for a particular momentum optimizer, here we show stochastic gradient descent with momentum, we can unroll the computation for a particular gradient update as such. And this gives us the update for a particular time step in this expression. If you view a particular G sub, let's say G sub J, for the gradient computed at a particular Jth step, and then consider the contribution of that particular gradient to all future steps as the steps tend to infinity, you get this geometric sum, which is beta over 1 minus beta. So in search of a simple decay rule, and Occam's razor, one way of implementing a momentum decay would be to decay this particular contribution to 0 as t tends to infinity. The number of steps tends to infinity, and give the algorithm schedule here. And there are two key results here. So one is the heat maps show that Demon is significantly more robust to hyperparameter tuning. So you can see for Demon, we get a significantly larger light patches, which demonstrate state-of-the-art performance for a variety of hyperparameters. The other important point is, given the same tuning budget and across a large range of hyperparameters and settings, Demon improves over their vanilla counterparts. And we have a large variety of settings, including image classification, language modeling, and other things.